All right, there's the recording, and then hold on. So
Are you listening?
AirPlay. I need to. It says that plugin is required. Okay, it's installing now. Okay, got it.
Okay.
Share screen via AirPlay.
Yes. You're just on your laptop, but you're using your iPad to.
Yeah.
I see.
Okay, screen mirroring. Zoom, and there we go.
Okay.
Nice. Oh, that's really nice.
We haven't done this one yet, right?
I don't believe so.
Okay.
Okay. All right. In a pumped storage hydroelectric system, water is stored in a dam of depth 34 meters. And then there's a pipe connecting the upper lake to lower lake. Okay. So water is out this way.
Yep.
And then water leaving the upper lake descends a vertical distance of 110 meters and then turns the turbine of the generator before exiting into the lower. Okay, got it. So flows out of the upper lake. 1.2 times meters volume per minute. Okay. Specific energy of the water. Yeah. And then energy density. So giving estimate the specific energy of water. So that means we would do so flow, the energy made by.
I always like to start off with what we're trying to find. So we're trying to find energy over mass, right?
Yes.
So then from there, I know what units I'm trying to get to.
Energy over mass. So we're given 1.2 times 10 to the 5. No, well, actually, wait for that. And then we have 1.2 times 10 to the 5 meters cubed per minute. Per minute. Oops. So that's volume over time. And then
the density of water is 10 to the 3 kilograms per meters cubed.
So if we multiply these two values, we'll get kilograms per minute, which is since it's mgh, which is energy.
Yep.
Right. So if we do mgh over time, then you get the power output. But
yes, so energy we find using mgh.
Yes.
So the height, what's the height that it falls? Let's see. Can we go back to the diagram?
It falls is 110
plus 17, right?
Plus 17.
Because all the water falls 110, but the average height for the 34 is 17, right?
Oh, okay, yeah. So it's.
I think so.
Oh man, no. Some of the questions about water are the ones that get me. So
yeah, you just have to. Okay, so you have to see what the whole thing is, what all the water is falling, and then what's only some of the water is falling. So that's why I think they divided it up. So I think it would be 127. It falls total.
So that essentially the average height of this is where we decide from.
Yes.
Where the water is falling from.
Yep.
Okay. Okay. So that means kilograms. So M times G. So kilograms per minute.
0. Let's just use G right now to make our calculations easier.
G. So this times G times H, which is 127 meters, is equal to power.
Yes. We need energy, so we need time.
So.
Okay. Where do we get the time from? Does it say how long it's running and how much time that?
I think I might have done something wrong.
Oh, it's specific energy, not energy over. It is energy over mass. So we need joules, right?
Oh,
In mgh. Here, can you write out the formula?
okay, yeah.
So energy is equal to mgh, right?
So in other words, we can do mgh over
Okay,
m.
then m's cancel. You're left with
M's
gh.
cancel.
So you
Oh,
don't
so we're
even.
just left with gh. Wow.
Yeah.
Okay.
Yeah.
So gh is
1 2
10.
Mhm.
So just put meters per second squared times h, which is 127 meters.
Mhm.
And that's, I guess, one, I don't have to do scientific notation. That's 1270 meters squared per second squared.
Yeah. So
Okay.
approximately 1300. So we're given 6 figs, right? 1300.
Yes. Is it, how many sig figs is it? One, two.
Well, for 9.8, right? It depends how, or 10 if you
Or
use 10
since
meters.
the given was 2, I do. You
Well,
do
we
2,
didn't
right?
use that for this calculation, but
Yeah, I guess so.
because of 10, it would be 1.3 times 10 to the 3 meters per or joules per kilogram, and we want to write it in terms of joules per kilogram.
Oh yeah.
Okay.
Wait, is
Yeah,
it?
so
We have
I
to
always
divide
start,
this.
yeah,
Oh
I
yeah,
always
no,
start
no.
with the formula because I mean at least an equation, because then sometimes things cancel and sometimes you don't need other stuff. That makes it a little bit easier.
Okay.
All right, next one.
Actually, I'll just take all of this away and then kind of move
Yeah,
the answer
sure.
up there. And then
Are you doing this on notes in iPad or where are you?
I'm doing Notability.
Okay.
Yeah.
Show that the average rate at which gravitational potential energy of water decreases is 2.5 gigawatts.
2.5. Okay.
So this is just at rate of energy change is power.
So okay. Potential energy.
We're looking at energy per time, right?
Is it power over time? Since potential energy. Okay. Yeah. So E over T, which is
E
just
over
power.
T. Now we're given E over. We just solved E over M.
Yeah.
We're
E over
given
M is 1.3 times
M over T.
We're given,
so if we're given E over M, right? We were given E over M. Or sorry. We just calculated E over M. And then they give us
M over T.
I think they actually give us volume over T, V over T.
Yeah.
So V over T. And then they also give us
Density.
M over V. Perfect.
So
things cancel just how we needed to. Yeah, that way you can see it clearly. Yes. So it's like a daisy chain, they cancel. So then you're just left with energy over time. But what we need is we actually need to use those values. So we just multiply all 3 values given in the problem and the one that we calculated, and then we get our value.
Is 1.3 times 10 to the 3 joules per kilogram times mass over volume is or I just do 10 to the 3 kilograms per cubic meter
cubed.
Times 1.2 times 10 to the 5 cubic meters per
minute.
Second. Minutes.
And it's in minutes. So that's another thing. We'll need to change the minutes to seconds later. Because otherwise we're not going to get 2.5 gigawatts.
Okay. Which should equal, if I do the calculation really quick.
It'll be, let's see, 13 times 12 is 1.56 times 10 to the 11. Is it 1.56 times 10 to the 11?
1, 2, 3, 4, 5, 6. Okay, I got as well. 1.56 times 10 to the 11.
1.56, right? Oh, if you round.
Okay.
Yeah. Sure.
Would we
10 to 11 joules per minute. Now we have to convert the minutes into seconds because otherwise we won't get in watts. So times
1 minute over
60 seconds.
60 seconds is equal to,
So 1.56 over 60.
divided by 60. That is equal to, if I move this all up really quick, that is equal to 2.6 times 10 to the 9. Is that what you got?
I don't know. I in front of me. So yeah. So that'll be 2.6 9. And the problem asks that you show that it's equal to what?
About 2.5 gigawatts. So.
Oh yeah. Oh, and then from there you have joules per second, which is approximately, yeah, exactly 2.5 times 2 gigawatts.
Okay.
Okay. I don't. They got 2.49. I think. I don't know how they got 2.49. Maybe it was just a calculating it. I don't know.
I think maybe they use 9.81.
Oh, that's right. Yeah. Okay. Oh, yeah, and also you'll get error carry forward, so it's fine. Okay.
Okay. So, if it's okay, I'll delete that.
Delete that.
And then
the storage system produces 1.8 gigawatts of electrical power. What's the efficiency?
Okay. So we just got potential energy. So we do 1.8 gigawatts over 2.5 gigawatts.
Exactly.
Which is 1.8 over 2.5, 0.72.
So about 72% efficiency, or you can write 0.7. That should work.
Oh, yeah, about 72% efficiency. Oops, there's a lot of noise in the background. Sorry. Okay. Give me 1 second.
Sure.
All right. Let's keep going. Let
me check the mark scheme for that one.
Oh yeah.
I think I'm pretty confident it's 70. I don't know how hard that would be. But
3. Yep, 1.8 over 2.5. 72%.
Okay. All right. So now let's go back.
Water is pumped back up at times when the demand for price of electricity is low. So
after the upper lake is emptied, it must be refilled with water from the lower lake, and this requires energy. Suggests how the operators of the storage system can still make a profit. That's like when you pump it back up at night, right, or something like that.
Yeah. With water. Okay, so this would just be bullet points, like a short answer kind of a thing.
Yeah. One. So I would just say it needs to be pumped back up. Is that but then how do they make a profit if it's pumped? That's actually a genuine question I had like in class. Like, how do they pump it back up and still make a profit? Like, don't you require the same amount of energy to pump it back up?
I would guess you would have to charge enough energy or make a surplus amount of energy that is enough to pump it back up, because a lot of the energy that the water goes back down, you won't need to pump all of it back up, I would assume.
Maybe.
Because usually reservoirs are already built into like naturally existing lakes and whatnot.
Mm-hmm. What does the mark scheme say for that one?
What does it say? Okay.
Water is pumped back up.
I read this when.
Okay. When the demand when the price for electricity, that's a very interesting concept. Wow. So you just whenever the price is lower, you just can pump it back up. Wow. Okay. Well, that must be it. See, I don't think I'm thinking purely physics. I'm not trying to think economics right now. No, but that's a valid thing to think about.
Okay. That makes sense. If the demand is low, that means they're not going to make a lot of money.
Anyway, so might as well use that time, like use that time to pump it back up.
Oh, okay, gotcha.
Yeah.
Part 1 is about the oscillation. Part 2 is about nucleus.
Part 1 isn't going to be on
Yeah.
Like that wouldn't be off.
Okay, nuclear fission, part 2.
This is a good one. That way we get a bit of water, we get a bit of nuclear. Okay.
9.5 times 10 to the 19 fissions take place every second. Each fission gives rise to 200 mega electron volts. That is the fission. Okay, overall efficiency is 32%. Contains a moderator and control rod. Explain the function of D.
Oh, that's kind of weird.
Yeah.
I think it's because they copy and pasted questions. Probably the first one was explain the function of the moderator and the control rods. We can just discuss that even if the answer is not there. But the function of the moderator is to slow down the neutrons to increase because neutrons have to hit the uranium nuclei with just the right speed. So we need to slow them down. And the moderator helps do that to continue the chain reaction and increase the energy produced. And the control
rod heats up once the fuel rods start to undergo fission. So then it would flow around that pump to transport to transfer some of that heat to the secondary circuit of water that gets boiled.
So that's what I was confused about. Is the moderator doing that, or is it like what exactly is being transferred?
I guess it's because the moderator and the what's it called, and the coolant, they're in the same like container of water, so they're actually the same thing, but they're not. So it's kind of like arbitrary.
To the different points in the process, I guess. Okay.
Yeah, that's a good way to put it.
The control rods just make sure that it doesn't turn into an atomic bomb. Okay. Outline why the math. Oh wait, we haven't been the first. Oh wait, it is right. It's just we haven't gone to the right question. A and B, all of those are for the first one, for the oscillation question. Yeah, so we need to go down. That's all. Oh, part E. There we go. So it was asking for the function of the moderator, the control rod in part E. And then I think we need to find D and E go with, D and E go with this question. They just broke it up weird. Anyways.
Yeah, 9.5. Okay.
Yeah.
So that's
part D is asking. Yeah. So, and also C, I think. But part D is asking determine the mass of uranium-235 that undergoes fission every day. So we're trying to find M. So our end goal is M, mass.
So M is equal to.
Can you do the calculations there, like further up? Because all the numbers are up there. So otherwise we'd have to go off. Yeah.
Where is it?
That's right there. Go back up. There you go.
Yeah. So let me zoom in. Okay. I'm just gonna kind of put it in whatever blank space I can find. So
sure.
M is equal to. So since we have the number of fissions, that's the number of nuclei. So 9.5 times 10 to the 19 things. See, in a question like this, you would need the molar mass though, right?
The molar mass, it's 235.
Oh yeah, you don't have to use it exactly.
Yeah.
Okay. Yeah,
it's not like chemistry where yeah.
So grams per mole. So we assume this is or amount. So actually we would have to divide this by Avogadro's number to find so 1 mole for every 6.02 times 10 to the 23 things.
That's how wait. I'm a little bit confused what we're doing. That's how many fish per second, right? The unit?
Yeah. So determine the amount of mass that undergoes fission. So if that many fissions goes place, that's how many particles are fissioning.
Yeah.
Okay. So that means, okay, let me do the quick calculation for that. 9.5 times 10 to the 19 divided by 6.02 times 10 to the 23. Okay, so this gets 0.000158 moles. And then we would do that, convert that to grams by using the molar mass. So 0.000158 moles times 235 grams per
Mhm.
every mole. These
Interesting.
cancel out.
I see what you.
Times 235.
I would do
That
point
gets.
kilograms. We're gonna need eventually.
Oh yeah. Okay. So 0.037. Two significant figures, right? Since it's 9.5 fissions. Okay, 0.037 grams.
Grams.
Then,
That's per second, right? So we need to multiply that by
kilograms per second.
or sorry, times 3,600 times 24. Yeah.
When it says determine the mass, did they typically ask for kilograms or?
Yeah, you would need
do.
to put grams, yeah, because that's the SI physics.
So times divided by 10 to the 3, which would just make it 3.7 times 10 to the so
-5.
Yeah, -5.
Okay.
1, 2
Kilograms.
Okay. So -5 kilograms.
Times
so that's
30,
per second. Per second.
Yeah, per second. Yep.
So
times 3,600 times 24.
3,600 seconds per hour times 24 hours per day. And that should equal, so divided by, then times 3,600 times 24 hours. Okay, which gets 3.20 kilograms per day. Checking that on the
That's
marks.
it. Now, Ashwin, I think an easier way to do that, I think the last part is the same, but I think to get to kilograms, what you might do instead of converting from moles, instead of using Avogadro's number, you could probably, I think, so the way I was thinking of doing it, and I don't know if this would work, yours makes sense, is if you use the number of fissions per day, and then convert that into number of fissions. Sorry, if you have number of fissions per second, if you convert that to number of fissions per day, right? And then you find the mass of, if you find the mass of one uranium atom in kilograms. So you start with 230. The mass of uranium. Sorry, the mass of uranium 235 is 235 U, right? So if you use the conversion factor for kilograms to U, then you could get kilograms right off of that. I mean, what you did works too. I think the other one might be less steps, but yeah.
U doesn't necessarily align with like 235. I guess it's such a small number. Work.
Yeah, for the purpose of this, yeah, I think
because we're assuming the same thing with molar mass, which is not.
Yes, exactly. So, exactly.
Yeah. Okay, gotcha. Mm-hmm. All right. Oh, I have to drop out for a bit, but
sure.
Come back and then.
Sure. You can scroll down just a bit and then just stay there. Just stay there. I'll just erase whatever's on there.
Oh, I have to actually leave the meeting.
That's
yeah.
Oh, all right.
I can come back around 5:15. So
5:15. Okay. All right. Mm-hmm. I'll keep working. I'll try and use my computer. I don't know, but maybe I'll just make a new recording. Okay. All right.
Sounds good.
See you.
And I'll stop the recording.